Your brain is like a massive, complex symphony orchestra, with billions of neurons firing in perfect harmony. To listen to this music, scientists and doctors use electroencephalography, or EEG. They place tiny microphones, called electrodes or channels, across the scalp to record the electrical melodies of the mind. But recording the brain is messy. In the real world, patients move, wires get bumped, and sensors lose connection. Suddenly, our beautiful symphony is interrupted by harsh static, or worse, complete silence from missing channels. We want to use artificial intelligence to decode these signals to help diagnose diseases or build brain-computer interfaces. But there is a major bottleneck. Traditional AI models are incredibly rigid. They require a fixed seating chart. If you hand them a recording with missing channels or a different electrode layout, the model breaks. To solve this bottleneck, the creators of ZUNA threw out the fixed seating chart. Instead of forcing the brain's symphony into a rigid grid, what if we just attached a precise GPS tracker to every single note? First, ZUNA acts like a digital metronome. It takes the continuous stream of electrical data from each channel and slices it into tiny, 0.125-second windows. Each of these short snapshots is packaged into a mathematical block, or token. Next comes the breakthrough. ZUNA stamps every single token with a 4D coordinate tag. It records the exact 3D physical location of the sensor on the scalp, the X, Y, and Z axes, along with its specific moment in time. This is called 4D Rotary Positional Encoding. Because of this simple mathematical tag, ZUNA no longer cares if it is fed 16 channels, 64 channels, or 256 channels. It just reads the tags. Now that the data is organized, ZUNA has to fill in the blanks. It uses an encoder-decoder system. First, the encoder gathers all the surviving healthy signals. It squeezes this massive amount of data into a dense, compressed summary of the brain's current state, capturing the deep correlations between different areas of the scalp. Where channels are missing or completely broken, ZUNA doesn't just try to draw a line connecting the dots. Instead, it starts with a completely blank canvas, pure, random static, also known as Gaussian noise. This is where the magic of diffusion happens. The decoder acts as a digital sculptor. Guided by the summary of the healthy channels and the exact 4D location of the missing sensor, it takes that pure static and iteratively chips away the noise. Step by step, it refines the chaos until a perfectly plausible brainwave emerges, perfectly in tune with the rest of the symphony. To understand the sculptor's chiseling process, we look at the math of diffusion models. The AI is trained by first learning how to destroy data, and then learning how to reverse that exact process, predicting how to remove noise step by step to arrive back at the clean data. This approach carries clear pros and cons. The iterative denoising leads to incredibly realistic data generation, but is computationally heavy. And while the latent bottleneck forces the AI to learn deep fundamental rules, if the input data is too sparse, it might hallucinate incorrect waves. Traditionally, scientists use a mathematical trick called spherical-spline interpolation to guess missing brain waves. It simply averages the signals from nearby sensors. If you only lose one or two sensors in a dense cluster, this geometric web works great. But if you lose most of your sensors, the gaps are too wide, and the math completely breaks down. This is where ZUNA's training pays off. Researchers tested ZUNA by intentionally deleting up to 90% of the EEG channels. As the data gets sparser, the traditional geometric method's error rate skyrockets. But ZUNA, relying on the deep patterns it learned from millions of hours of brainwaves, consistently outputs highly accurate reconstructions. The wider the gap, the bigger ZUNA's advantage. What does this mean for the future? Because ZUNA doesn't just fix broken channels, it can imagine channels that were never there. We call this super resolution. By upsampling the data from cheap, comfortable, everyday consumer headsets, ZUNA could give researchers access to clinical-grade brain maps anywhere in the world. While generative AI like ZUNA offers incredible advantages in handling massive dropout and enabling super resolution, we must remember the data layer caveats. These imputed channels are highly realistic estimates, not absolute ground truth measurements for critical clinical diagnoses.